Today we're going to start on 13.4, which is a connected rate of change. So we have learned about the chain rule. So today the very first thing, right, is that we learn that the rates of change can be connected. So one of the most important relationships, right, for this chapter would be this. If you want to find the rate of change of y with respect to time, okay, it follows that it is the product of you differentiate y with respect to x, multiply to, you differentiate or you find the rate of change of x with respect to time itself. Okay, I know that this looks like some kind of equation whereby it's like a fraction and you can cover, you can just eliminate so that you get dy dt in this case, but it is not. Okay, in this case what we actually know is that the rate of change of y with respect to time is the rate of change of y with respect to x multiplied to the rate of change of x with respect to t. So this is something that you need to be able to form, okay, this relationship, right, in order to solve these questions involving the connected rates of change. I think that I will go into an example now, okay, to actually help you with this. So let's go and look at example 6. If you can see, this actually occurs on your textbook, book B on page 37. So it says this, that the equation of a curve is given as that, find the rate of change of y when x is 2 and x equals 10, given that x is increasing at a constant rate of 4 units per second. What helps me, okay, when trying to solve these questions is to actually write it out first. So rates of change of y, you are basically trying to look for the rate of change of y with respect to time, okay. When x is 2, x is 10, these are some values, and it's given, okay, that x is increasing at a constant rate of 4 units per second. So it means this, the rate of change of x with respect to time is equals to 4 units. If you remember from our previous from our previous slide, rate of change of y with respect to time, okay, by the chain rule is differentiate y with respect to x and take the product of it and the rate of change of x with respect to time. So this is what we'll be applying for this question. So immediately what I can do here is this. First, I'll differentiate y with respect to x. I'm differentiating this guy. So what we can do is we apply the product rule, v du dx. So it's v, okay, times du dx, then plus u dv dx. So if you differentiate this dv dx, very quickly what you get is 1 over 2 square root of x minus 1. So if I just simplify this, I get root of x minus 1 plus x minus 7 over 2 root of x minus 1. You can leave it in this form, it's perfectly fine, but in this case I just choose to simplify. So once again, if you just leave it like this, it's okay, you actually work with the what I call unsimplified value. But if I choose to simplify and combine into a single fraction, I will get this. Okay, I have my value of my my expression for dy dx. So now if I want to find, okay, rate of change of y with respect to t, and this one occurs when my x value is equals to 2. So I take dy dx, which is here, I sub in the value of 2. Okay, I multiply this to dx dt, okay, which is here, which is 4. And if I just work everything out with my calculator, so what I should get down here should be the value of -6. So it means that y is decreasing at a rate of 6 units per second, okay, when the x value equals to 2. Similarly, if I were to find the rate of change of y, okay, in this case, when my x value is equals to 10. So similarly, what I get is 3 times 10 minus 9 divided by 2 times square root of 10 minus 1 times 4. Because the rate of change of x with respect to time is always 4. If you work everything out, it is 14. So it means that when the x value equals to 10, the rate of change of y with respect to t is 14 units per second, is increasing. While in the previous portion, when x value equals to 2, the value of y is actually decreasing at 6 units per second. I urge you now to pause the video and to try 6. Okay, try 6 occurs on page 37 of your textbook. So if you need a textbook, if you need a textbook, it's at page 36. And I will give you the solution in 3, 2, 1. Let's go. Okay, first they ask you to find dy dx. So for this one, quite simple. V, okay, times du dx plus u times dv dx. Then what you do here is, because of this denominator for this term, I multiply him by 2x plus 5, 2 root of 2x plus 5. Then if you simplify everything, okay, what you will get is this step, and then it will actually simplify. Alright, okay, sorry, this one will eliminate the 2 and 2. So the lowest common denominator is root of 2x plus 5. So to this term, I multiply by this, and I combine my fraction down here. It simplifies to this 3x minus 4 divided by root of 2x plus 5. So in part 2, what they want is to find the rate of change of y. So let me write down what they need us to find. We need to find rate of change of y with respect to t. Okay, given that x is increasing at a constant rate of 2 units per second. Application of the chain rule will provide this. I told you one of the most important relationships in this chapter. So dy dx was found previously. So rate of change of y with respect to t, dy dx is here, multiplied to dx dt. I get this expression here. So when x value equals to 2, you just sub in the values. You find the rate of change of y with respect to t is 1 1/3 units per second, is increasing. Similarly, when x equals to 5.5, I sub into the expression I obtained above. What I get is 6.25. That means that when x equals to 5.5, the rate of change of y is 6.25 units per second. Y is increasing. Okay, now I will speak about example 7. Example 7 can be found on your textbook on page 38. So it talks about the radius of a circle. So what we need to know here is this. The radius of a circle increases at a constant rate of 2 cm per second. So area. So we know about circle, and then we know area. So what I can write here is this. The area of a circle is given by something we have learned in primary school, pi r squared. Constant rate of 2 cm per second, it means that the rate of change of the radius with respect to time is positive 2 cm per second. So now, okay, what we can do here is this. First, I can find the rate of change of A with respect to R. So what I get is 2 pi R. Now, I want to find the rate of increase of the area. So what we need to do here is this. We need to create that relationship. So for example, in the previous example, dy dt equals to dy dx times dx dt. Okay, over here, this relationship here. So now, okay, we are not dealing with y. So instead of y, what we're dealing with is a. Okay, so dA dt is dA dr, okay, because now we have the r times dr dt. So you have to make amendments to that equation that we learned previously. So what I can write down here is this. I will write dA dt, that's what they want, is equals to the rate of change of area, you differentiate area with respect to radius, multiplied to the rate of change of radius per unit time, which we know from above to be 2 seconds. So dA dr is 2 pi r, okay, times 2. So what I get is 4 pi r. So this one is simple enough, okay? So they ask you in part 1 when the radius is 6. So when radius is 6, very simply, my rate of change of area per unit time is 4 times pi times 6. So what I get is 24 pi. So it simply means that when the radius is 6 cm, the area is increasing at 24 pi cm square per second. Okay, part 2, the area is 9 pi cm. So this one, we can still use what we have from the previous part. So from the previous part, I know that my dA dt I found from part 1 itself is equals to 4 pi r. So now the issue is I don't have the radius. If I want to find the rate of change of area when the area is 9 pi cm, so we need to actually do a bit of working to actually obtain my radius. So I know that area is pi r square. I also know that at this point in time, my area is equals to 9 pi. So what I can do here is I will equate them. So r square is 9, my radius is equals to 3 cm. So basically when the area is 9 pi cm square, the radius is 3 cm. Now that I know this, what I can do here is to attempt to find the the rate of change of area with respect to time. So 4 pi r, so 4 pi, then the r is here. Okay, the r I know is 3, so it's 12 pi. This means that when my area is 9 pi cm, the radius is 3 cm, and at this moment in time when the radius is 3 cm, the rate of change of area with respect to time is 12 pi cm square per second. Okay, please pause the video now and attempt to do try 7. This can be found on page 38, okay, of your textbook volume B, and when you're done you can unpause the video and I will carry on to give the example in 3, 2, 1. Okay, first and foremost, okay, air is let out of a spherical balloon at a rate of 300 cm cubed per second. So what I can say is that air, what is air? Air is volume. So I know that the rate of change of volume with respect to time is equals to negative 300 cm cubed per second. So now they ask you to find the rate of decrease of the radius. So what we are actually looking for here is rate of change of radius with respect to time. Okay, now we need to work some things out now. Okay, I know that when I have a volume, in this case is volume of a sphere, you need to memorize is 4 over 3 pi r cubed. So if I differentiate the volume with respect to radius, what I get is 4 pi r square. Okay, see okay, now, okay, I got 3 things here. I got rate of change of volume with respect to time, rate of change of radius with respect to time, and I got you're differentiating v with respect to r. How can I fit them so that they form an equation? So basically this, okay, if I look, all right, down here, okay, where is down here? Down here is here, okay. I know we cannot eliminate, but how they fit is dr and dr in your brain, they will be able to eliminate. It's not correct mathematics, but it helps you to form the equation. So if you eliminate this, you'll get dv over dt. So that's how I form the equation here. So I'll say that dv dt equals to dr dt, rate of change of radius with respect to time, multiplied to dv dr. Or what they did right in this question is they flip them around. So what I mean by flip around is they put this and this like this. It's still the same thing. So I just stuck in the values that I know. So I know that the rate of change of volume with respect to time is negative 300. The VDR is negative is equal to 4 pi r square multiplied to rate of change of radius with respect to time. You simplify, divide by 4 pi r square, divide by 4 pi r square. you find the rate of change of radius with respect to time is given by this expression. Dividing by 4 on my numerator, and denominator gives me this simplified version over here. Now, part 1 is simple enough when the radius is 2 cm. So radius is 2 cm. I substitute the value. I get that rate of change of radius with respect to time is negative 75 over 4 pi. So it means this, where the radius is 6 cm, the negative means that the radius is decreasing. So the radius is decreasing at a rate of 75 over 4 pi cm per second. The negative means it's decreasing at a rate of this. Okay, now part 2. So part 2, they tell you the volume is 36 pi. So as I said earlier, the volume of a sphere, which you need to memorize, is 4 over 3 pi r cubed. So that's equals to the volume. So if I solve, okay, I find that my radius is equals to 3 cm. So from the earlier part, we know that rate of change of radius with respect to time is given by negative 75 over pi r squared. I will substitute the value of r to be equals to 3. I will get this value here. So it implies this, that when the volume is 36 pi, the cm cube, the radius is 3 cm. When the radius is 3 cm, it means that the rate, as we sub into the expression, we found that the rate of change of radius with respect to time is negative 25 over 3 pi cm per second. And that's it for